Hello, I'm Dr. Bill Curtis, the Director of the Consortium for IT Software Quality, which is co-sponsored by the Object Management Group and the Software Engineering Institute. Software engineering, just like medicine, is now suffering a new, more virulent strain of bugs than we've faced before. Like medicine, we've gotten very good at detecting and eliminating the simple bugs, the ones that just inhabit a single component or a few components that are within the same technology or language. But just as in medicine, we're starting to see a new strain of virulent bugs that are resistant to the kinds of technologies we've used in the past for detecting and eliminating them. Bugs in medicine have become resistant to modern antibiotics, and in software, these bugs are starting to be seen across the multiple languages and technologies from which we construct modern IT systems. The problem is that in order to manage the complexity, the growing complexity of the kinds of IT systems that we're building, we started building different components in languages and technologies that were specific to the kinds of functions being performed. For instance, a different language or technology for the user interface, for the data logic, for managing data access and data storage, or for managing communication with ERP systems or legacy applications. Each of these can be built in a very different language with a different technology, and the problem this causes for us is that there's no single developer or even team of developers who understands all of it. Consequently, they have to make assumptions about how their components are going to interact with other parts of the systems and how those parts of the systems are going to work. The problem is that although most of their assumptions are correct, some of those assumptions are wrong, and that leads to some of the most devastating operational defects we've seen. Let me give you a few examples. First, think of a situation where I have someone entering through the user interface, but the path goes straight to data storage and avoids data authentication or approved data access methods. Consequently, we can either see a breach of security or we can see data corruption. Think of a loop in which we have a very expensive operation, but it just so happens that that's operating on a very large data table, and so we see strong degradation of performance. These are the kinds of problems that we're seeing, and that you have to analyze the entire system and all of its components in the different languages in order to detect. What we're seeing now is that the worst bugs we're facing have gravitated upstream. They now sit in the interactions between different technologies and different languages. In order to detect these kinds of defects, we have to perform a different level of analysis than we have in the past. Traditional testing methods, traditional component-level static analysis are not adequate to detect these kinds of defects. What we have to be able to do is look at the entire system, analyze it across all of the languages and technologies to detect these kinds of defects and flaws that sit within the different parts of the system and their interactions. Research is telling us that these architecturally complex defects, although accounting for sometimes as little as 10% of the defects in the system, typically take at least half of the effort to repair, so they're extremely costly compared to other defects. Experience in the field and logs we're seeing on major outages and other kinds of operational problems are now suggesting that these architecturally complex defects can account for as much as 90% of all the major operational problems we're seeing in large IT systems. So in order to be able to solve the problems we're now seeing in the kinds of complex, multi-language, multi-layer, multi-technology systems that we're building, we have to upgrade the level of analysis that we're performing to detect the defects. We'll continue to do traditional testing, traditional component and technology level analysis. But in order to stop the problems we're having, we have to upgrade the level of analysis to the system level and be able to analyze these system interactions as well. In order to aid this, the Consortium for IT Software Quality has recently defined a set of metrics, a set of measures for maintainability, reliability, security, and performance efficiency. And these are based on some of the most complex defects that we have been able to understand and find, and that we measure how many of those are in the system and provide a corporation or a system owner with better information on how reliable their system is going to be in operation based on being able to detect not only simple defects, but also these architecturally complex defects. I recommend the tech report to you, the new CISQ standard for these kinds of system level measures. You can get them on the website at CISQ at www.it-cisq.org, or you can also get them on the OMG website as well as a number of other forms of information that will be valuable. There's also a report that describes how to use these in operation that you can get either from the CISQ website or the OMG website. So again, I recommend that you help upgrade your level of system analysis so that you can detect these more virulent architectural level defects. And I wish you good luck in doing that. Certainly your customers will appreciate the fact that you did.